Welcome to lecture number 5 of module 2. In this module, as its name is Equipment and Stability Constraints in Power System Operation. So, this lecture is completely devoted to the stability definition, concepts and its fundamentals, and we will see that what are the various stability concerns and their definitions, why they are very important for the power system operation and control. To introduce with this definition, let us see why this stability is required at all, this stability analysis as I mean. Power system stability has been recognized as an important problem for secure operation of system since 1920s. In 1920s, there was the first case of the system instability, and after that it has gained momentum, and now we are having a lot of instability and instability analysis of the system to say that your system is stable or not. Historically, the transient stability has been the dominant stability problem on most systems and has been the focus of much of the industry's attention concerning the system instability. In early days, the people were only recognizing the instability phenomena is as a transient instability. So, they were concerning in terms of their analysis, their mitigation and their other related issues on only the transient stability. But due to the increased interconnections, stress power system, that is keep on loading and the keep on interconnections, the voltage stability as well as the frequency stability, that even though along with the inter-area oscillations have become greater concern than in the past. And as I said, it is due to the more and more interconnections, highly loaded and the complex power system, the voltage stability, frequency stability and the inter-area oscillations are also very important, and that's why we have to go for the various stability analysis. A clear understanding of the different type of instability and how they are interrelated is essential for the satisfactory design and operation of power system. So, we have to understand what are the various instability problems and how they are interrelated. That is very important for the power system design and operation. Means you have to design a power system that should be stable and you should operate your power system in a stable manner. Along with the other criteria, already we have seen that the power system design and operation criteria include your power system, the quality, power system security, the stability, reliability, and also just we should operate the power system in the least economic way, means economical fashion, so that the cost of electricity is cheap, uninterruptible, and it should be better usable in terms of customers use. As well, consistent use of terminologies is required for the developing system design and operating criteria, standards, analytical tools and the study procedures. So, the problem of defining and classifying power system stability has been addressed by the several previous SIGRE and IEEE task force reports. Here IEEE, this Institution of Electrical and Electronics Engineers task force, so they have already defined, but again it is keep on reviewing this, and again those early days means that these earlier efforts however do not completely reflect the current industry needs of now. So, we have to go for the clear definition again based on the industry needs, experiences and the understanding. In particular, the definitions are not precise because in the previous definitions were not precise, and the classification do not encompasses all practical instability scenario. As I said in the beginning, only we were concerned about the transient stability. Later on, we introduced the dynamic stability, steady state instability and also the voltage instability. But nowadays again some more instability, and their basis may be a time frame, depends upon the disturbance nature and so on and so forth. So, we have to define and understand the various instability and stability phenomena in the power system. So, that is why this has created a need to review the definition and the classification of power system stability. So, we want the power system stable in terms of designing, in terms of operation. So, whatever the kind of instability in the power system is, that must be reduced, that must be removed, so that we can have the secure and stable operation of the power system. If we will see the power system stability old definition, as per the, it is a property of a dynamical system or its ability to remain in a state of operating equilibrium. This is very important, operating equilibrium under the normal operating condition, and to regain an acceptable state of equilibrium, another equilibrium here, after being subjected to a disturbance. To understand this, let us see here, let us suppose in a multi here directional plane, you are here, your power system is operating at this point. So, this point is stable initially in the normal condition, and if there is a disturbance in the system and your system is moving to another system here, that is also stable. But there is a possibility that this trajectory, this state is stable, this state is stable, but it may not always possible that the transition from this stable A to stable B is possible. So, it may be possible that this may go somewhere else, and then we can say our system is unstable. We know that this is your pre-fault condition, initial normal condition where your system is operating. If there is any disturbance, then your system should go to another stable point B. B may be the different, again it depends upon the system scenario, change in the topology, change in the generation and the load scenario. It may be the same A point, of course, but the disturbance one, it is clear, then your system must go to the another stable point B, then we can say the system is stable if it is coming to this point here through any region. But there is a possibility that this point, no doubt the post disturbance is stable, your initial is stable, but your system can go somewhere else. It is not coming to your stable point, because it is time which is coming, keep on going, and finally it is unstable. So, here that is why it is in definition, it is said that your operating equilibrium under the normal operating condition means initial condition. Your system is in the equilibrium point and it should regain a acceptable state of equilibrium after subjected to disturbance. So, this is means it should come here the stable, then we can say our system is stable. If this is not, then it will be go away. Now, the new definition has been given recently. There was again another IEEE task force, it gives the again concise definition of the power system stability. It includes all the stability concerns, and the various stability analysis techniques are given in that paper, and this is again this committee was headed by the Prabhak Kundur, and even though you can see his book, the stability is very he has defined all the stability in the very precise manner. So, as per new definition, the power system stability is the ability of an electric power system for a given initial operating. Here they have written the initial, earlier it was the normal operating, but normal means the system at which your system is operating. So, it is better to say that initial operating condition to regain a state of operating equilibrium after being subjected to a physical disturbance. Again, the physical disturbance is of different types. Again, there may be some fault, some loss of load, something happening, you can say loss of power, transmission line tripping, short circuit, etc. So, if there is any disturbance, then it should regain another stable operating equilibrium with the most system variable bounded, so that the practically the entire system remain intact. So, your system should not lose the synchronism and it should be in stable condition. The stability basically depends, now we can now realize, on depends upon here initial operating condition and the nature and the amount of disturbance. Again, the amount of which type, for example, of a small change in the load is another type. There may be a severe load change, there may be a small change in generation, there may be severe change in the generator, means suppose there is one generator is out. Another, the nature, it may be the power outage, it may be load change, it may be the short circuit, it may be the tripping of the transmission line, it may be the tripping of any other equipment in the power system. So, the stability in total depends upon the initial state where your system is operating right now, although it is no doubt it is stable, but at what level, means at which point, how close to the unstable position, and then the nature and the amount of the disturbance. We saw this power system security as well in our beginning lectures in the module 1, what is the power system security. So, to recap it, security is a term used to reflect a power system's ability to meet its load demand without unduly stressing its apparatus or allowing network variable to stay from the prescribed range. Here this security is one step ahead. There is a possibility that your system here, for example, your just a simple, your here you are operating at here the voltage well within limit and your system is stable. Now, after the fault, after the disturbance, you have reached another point B, where this your V is not, means here this is you are not satisfying its limit, that is a V limit upper, and here it is your V lower limit. So, system is stable, but it is violating the operating constraints. In this case, I have taken the voltage. It may be your line flows, it may be overloading of the line flow as well, it may be violation of the reactive power limits, and so on and so forth. So, this point is stable, this point is stable. In terms of stability, we can say our system is stable, but in terms of security, here this point is stable, this point is stable, but system is not secure. So, it is one step ahead, where we have to check the operating limits as well, that it should be well within limit. So, that is your power system security. So, already we defined the power system security and we gave the different kinds of security in terms of line or megawatt security or reactive power or voltage security, and then we gave the several states based on the security, that is a normal state, secure state, alert state, emergency state, restorative and expensive, and so on and so forth. So, you can see this security is one step ahead than your stability. Now, this power system stability again can be classified in the different way, different again depends upon the quantity which you are monitoring, and that can be, one is your angle, another here that is called your angle, it may be your frequency, it may be your voltage. So, if your monitoring quantity is your angle, then it is called your rotor angle stability. Means monitoring means what? I want to say means this parameter is more concerned than other these two parameters. Then we can say this is a rotor angle stability. And you know this rotor angle stability is directly angle. Here this is related with directly your real power flow. However, this voltage is directly related to your reactive power. You will see later. So, the rotor angle stability is a ability of interconnected synchronous machines of a power system to remain in synchronism after being subjected to a disturbance. So, whenever there is a disturbance, so your whole operating system, including your synchronous machines, your whole intact system must be in synchronism, then we can say it is a rotor angle stability of the system. Now, what is the voltage? Here our monitoring quantity is the voltage rather than delta. So, the voltage stability is the ability of the system to maintain voltage, so that when load admittance is increased, load power will increase, and so that both voltage and power are controllable. What is the voltage stability? To understand this is very way. If you will see the two bus system, this is your real power, this is your voltage, and if you draw the PV curve, we will come to this voltage stability in detail in later lectures of this module, we will come detail. So, better to understand here, let us see this is a voltage variation. We have a system, let us suppose a generator, and here we have a transmission line, and this is your infinite bus, or you can say here we have a load here. So, we can draw the power which is flowing here. If you will keep on increasing, that is here load, then the voltage at this terminal, this is your slack bus, this V we can draw as per this characteristic. What does it mean? It shows that for one power, let us suppose P naught here, you have two voltages here as well as here, one voltage here, another voltage. Now, which one is your operating voltage? Which zone is stable, which zone is unstable? You can see the topmost, when the power is increasing, your voltage is decreasing, that is obvious. But in this case you can see if your power is increasing, the lower portion, this point is called nose point. So, the lower portion, if your power is increasing, voltage is increasing. So, this is a reverse one. And here what is happening, your admittance is increased when your load power is increased. So, this zone, the lower section here is called unstable, and it is, you can say, the voltage instability in this zone, only operating voltage will be in this zone. So, this is related with the voltage. When we monitor the quantity, where quantity of concern is much voltage than your delta and the frequency, then it is called voltage stability. Another term is widely used, that is voltage collapse. People say the system is collapse or blackout, whether due to the angle stability or whether due to the voltage. So, voltage collapse is the process by which voltage instability leads to a blackout or very low voltage profile in a significant part of the system. Means when the system voltage go beyond its permissible limit and it is persisting for a longer time, and then it is called the voltage collapse. It may lead to sometimes the blackout in that area. So, this is your voltage collapse definition. Now, the frequency stability, as I said, the three terms, delta, voltage and frequency. So, the delta is related to your angle stability, the voltage is related to your voltage stability, and the frequency is related to your frequency stability. No doubt the delta and the frequency are directly related with the real power. However, the voltage is related to your reactive power. So, when we are just talking about the delta, we are observing the delta of the machines, it is basically angular stability. When we are talking the frequency, where the delta everything is in normal state, but frequency is changing, that is severely, then it is your frequency stability. So, the frequency stability refers to the ability of a system to maintain steady state frequency following a severe system upset, resulting in a significant imbalance between generation and load. Basically, the frequency stability is concerned with this imbalance in the power. Means this instability occurs when there is a severe surge, severe outage of your system generation and etc. So, what normally we do, we go for the islanding of the power system. So, there may be possibility one island may not having the balance reserves, balance supply, and that may have the frequency instability. So, this is basically the severe surge whenever arise, then the frequency instability term comes into the picture. Let us see the again the voltage stability, voltage instability and the voltage collapse definition as per the Segre. Voltage stability, a power system at a given operating state and subject to a given disturbance. Disturbance includes your fault, maybe variety of faults, you know, is a line to ground fault, LL fault, triple LG fault. So, all the various of faults, tripping of the heavily loaded transmission line, outage of power generators. So, all these are the disturbances. Is voltage stable if voltages near the load approach post disturbance equilibrium values, the disturbed state is within the region of attraction of stable post disturbance equilibrium. Means here once the disturbance is there, initially your system is operating in the stable mode without violating the voltage, and after the disturbance, if the voltage are also well within limit, then it is called, and that equilibrium is must be stable, then we can say it is a voltage stable and your system is a voltage stability is there. However, the instability is the opposite of the stability. The voltage instability is the absence of voltage stability, means there is no voltage stability, and result in the progressive voltage decrease or increase in both sides. There may be voltage excessive increase, there may be voltage decrease, destabilizing controls reaching limit or other control actions like load connections, load shedding, however, may establish the global stability. Here in the voltage instability, what happens? There is a possibility that the voltage of the fewer area, certain zone may increase or decrease heavily and that may destabilize the control actions. You know, we have a lot of devices, those are working on the voltage measurement. If the voltage is less, so under voltage relay may operate, picked up, and that may give a trip command to the load setting, etc. Because under voltage or under frequency, the relays are there and they are normally go for the load setting, etc. So it may go for the load disconnection. Then what will happen? Then it is called the voltage instability. Means voltage has gone excessively down or higher than its prescribed limit. So the voltage collapse as per Segre definition, the following voltage instability: a power system undergoes the voltage collapse if the post disturbance equilibrium voltage near loads are below the acceptable limits. Acceptable limits, here it is not only this operating limits. We can operate the system smoothly even though outer than your voltage limit. As I said, the voltage limit here should be plus minus 5% for EHV lines. But if the voltage here is more than 6, 7, 8%, it will not hamper your system stability. Your system can operate, but we don't want to operate because that is a stress and that may lead to the instability phenomena later on. So it is the acceptable limits. Normally it is again depends upon the system to system, how stress your system, at what loading your system is operating, that is defined. So the voltage collapse in a system may be either total, that is total blackout, or it is a partial. Partial, again it is a very confucius, and for whole, let's suppose for our Indian case, we have the, as I said in the previous lectures, that we have the 5 regions. We have the northern NREB, normally say Northern Regional Electricity Board, we have Eastern Regional Electricity Board, we have Western, we have Southern, we have Northeastern as well as the Eastern. So we have 5 regions. So in all the regions, other states are connected. Like in Northern Uttar Pradesh, people are connected in the northern region. It is your Rajasthan, Haryana, Punjab, your Jammu and Kashmir, and Himachal Pradesh. Of course, Delhi is also inside that. So they are connected. So what happens? There may be possibility that few portion of whole this northern region is in out, means in dark, blackout. So it is called the partial. If whole this region has gone, then it is a complete blackout. Even though some of the feeders, those are feeding to some village, some area, some municipality, something your urban area, and that feeder has gone due to the instability and other problems, then it is called the partial. So your this voltage collapse may be your partial or complete. Again, it is due to the voltage if it is beyond the acceptable limits. So the stability general definitions, let us see what is the stability phenomena. Basically the stability can be defined, can be understood by looking at the condition of equilibrium of 2 opposite forces. So stability phenomena basically can be realized by understanding the condition of equilibrium between 2 opposite forces. To understand this, here for any system here, let us suppose you have a mass here, this let us suppose is rotating. So to hold it, if one direction of torque is this and another is opposite, then it will not rotate and the system will be intact. Simple for one revolving, if you are having one force here, then it will keep on moving, unidirectional. But if you have another force that is trying to resist it, and if both are equal, here let us suppose it is the T1 and your it is the T2. If your T1 is equal to your T2, then we can say the system is stable, it is not moving. If one force is there, another force is opposite. But there is a possibility if any one of this is increasing and it's not, this equation is not satisfied, it is not this, then it will be having one motion in any direction. Here again, if T1 is more than T2, then it will be rotating in this direction, otherwise it T2. So it is basically the equilibrium condition of 2 opposing forces. During the steady state, the mechanical torque is equal to the electrical torque. In the now come to the machine part, normally this T1 is nothing but your Tm and this is your Te. Tm is the, in any machine, here let us suppose your synchronous machine here, what happens, here we give here the mechanical power and we get our electrical power. Means the power once the system is rotating, is the rotating mass, and this power we can say we have the torque that mechanical torque, and here we are getting the electrical torque. So, if both during the steady state the Tm is equal to your T, and then it is called the steady state. But during the disturbance, this relation may not satisfy, and again as one system is stable, we will get this condition satisfied. So, during that disturbance period, when this is not satisfying, what will be the system behavior, and that is basically we have to study the behavioral system during that one. Means we have the three conditions. One is called your pre-fault condition, another is during fault condition, and third one is your post fault. So, these conditions here, the pre-fault condition, it is satisfying this Tm is equal to T. Your post fault must also satisfy this. If it is not satisfying, means your post fault system is not in equilibrium condition. So, the pre-fault and the post fault is in equilibrium condition, but during the fault, means as I said, in the multi-directional here, multi-variable space, your point here is your the pre-fault condition A, the post-fault condition here is B. Now, during fault, whether your system is coming here with the following trajectory, or it is going somewhere else, or unstable condition. So, basically the stability phenomena is related with the what is the condition here. It is also very much depends upon what is the condition of your pre-fault, what is your condition of your post-fault, and during what is your condition, what is your system behavior. So, we try to analyze these trajectories. If you can get this trajectory in the time domain, then we can say and we can judge that whether system is stable or unstable. So, the change in electrical torque of synchronous machine following perturbation or disturbance can be resolved into two components. There are two components that change in the electrical torque. Whenever there is a fault in the system, as I said here, if there is some fault in the system, let us suppose this is generator and it is connected with your power system. If there is any fault in the system, this P or you can say T will be changed. So, the change in this T will be related with this equation. Means we have two components. One component is called the synchronizing component. This is your synchronizing component or synchronizing torque, and another is your damping torque. The damping torque, that is Td here, it is in phase with the change in the speed deviation. However, your the synchronizing torque, that is in phase with your angle deviation, difference in angle. So, the lack of sufficient synchronizing torque results in instability through aperiodic drift in the rotor angle. Means if there is a lack of your synchronizing torque Ts, then it will give you this change in delta which is moving, and it is aperiodic. Means your system here like this, it may be from here, it may go like this, it will be not, you can say, not oscillatory in nature. So, it is aperiodic drift, aperiodic change. Another component is your Td del omega is the damping torque, and this damping torque basically if there is a insufficient damping torque, then that will result in the oscillatory instability. Means your system here will be what will be going, it will be keep on increasing and it will be oscillating, because it is a change in the speed here and means change in the delta. If speed is changing, so change in delta is also there. So, the rotor angle instability can be categorized into the two based on the large or smaller disturbance, and those are here I can say small signal, or we will see the transient stability. There is two type of rotor angle instability. One is your small signal stability. Basically in this we analyze with the small disturbance. Small disturbance is nothing but change in your load and change in generation. This is small, but the certain amount is small, but certain change, and it is always happening in the power system. because in the power system, you know, this load is keep on changing and generation is following that. So generation and load are keep on changing, and that is always there in the system. So we have to analyze the behavior of system with these changes, and that is always there. So the small signal, as also known as the small disturbance stability, is the ability of power system to maintain synchronism under small but sudden. So that's why here I am saying it's a small but sudden disturbances, and those are always present due to the change in load and generation. In this case, the system equations are linearized due to the small disturbance. Means we have to linearize, as you know, the power system is the nonlinear equations, nonlinear phenomena. So those nonlinearity can be linearized, and then stability can be studied. Instability that may result can be of two forms. Means it again it can be two forms. One is the steady increase in the rotor angle due to lack of synchronizing torque. As I said, the synchronizing torque, that is your Ts here delta S, and another is your rotor oscillation of increased amplitude due to the lack of sufficient damping torque, that is Td del omega. So it can be due to this region and it can be with this region. So this is no doubt it is oscillating, and you can see here here it is keep on increasing with the oscillation and system become unstable. Here your angle basically keep on drifting to change in delta continuously, it is a periodic change, and that is due to the lack of synchronizing torque. Normally the first one means, if you will see, the without AVR, the constant field voltage, that is the instability, is due to the lack of sufficient synchronizing torque, that is non-stability. So the previous, as I said, the lack of synchronizing torque will give your aperiodic drift of the rotor angle if there will be no AVR, automatic voltage regulators. But nowadays modern power system, they are having automatic voltage regulators. So that type of concept here, this is normally is not happening. So only the small signal stability is of this concern, and we always go for the oscillatory type of instability appears. So with the AVR, that is the automatic voltage regulators, means excitation system. Automatic voltage regulation means we have to control the voltage automatically, and that is basically due to the excitation system that is available with the generators. So all the modern generators, they are equipped with the AVRs. So the instability with the AVR is normally through oscillations of increasing amplitude, means the second type of here small signal instability. Again, this small signal stability can be classified into the two forms, not two forms, it is four forms. That is, first one is your local mode, are sometimes also called the machine system modes. Another is your inter area modes, third one is your control modes, and fourth one is your torsional modes of oscillation. Now let us see what is your local mode. The local modes are associated with the swinging of units at a generating station with respect to the rest of the power system. The local means localized at one or a small part of the system, and this frequency of oscillation is normally 0.7 to 2 hertz. To understand this, here let us suppose here a power station, let us suppose we have a Obra power station, that is thermal power station we have. This is generator at Obra. It is not one, there are so many generators at Obra, means we have here 4 into 200, we have 5 into 200, yes, and then we have again 3 into 100, and also we have the 50, and those are not working nowadays, and it is connected with the rest of the UP and this NRB system. What happens? We have other generators here, we have other generators here in the system, we have more than 40-50 generators in NRB region. So if the any one of the units here at Obra is oscillating with respect to other system here, means you can take this system as a standstill, and then you can see the oscillation in this any unit of Obra, then we can say it is a local mode oscillation. Another one is your inter-area modes. Inter-area modes of oscillations are associated with the swinging of many machines in one part of the system against the machines in another part of the system, and two or more groups are connected with the weak tie line, and this stability oscillation is normally 0.1 to 0.7 hertz. To understand this, here for example, let us suppose we have a one area here and another area here, means we have here UPPCL, here we have a Rajasthan State Electricity Board, and we have the several lines, those are connected with a different one. So, there is a possibility the generators in this area and the generators here, they are oscillating to each other. So, it is inter area, and this is due to the weak tie line between these two neighbors. So, it is called inter area modes of oscillation. So, the difference between your local mode means one unit of any power plant is oscillating with the rest of the system, and that here it is 0.7 to 2 hertz, and here in the inter area modes of oscillation, the one area may be your few generators, may be a complete state, these generators in that area are oscillating with here the generators in another area. So, it is called inter area. Another term here, that is called control modes of oscillation. The control modes of oscillation are associated with the generating units and the other controls. The poorly tuned excitation system, governors, HVDC converters, SBC are usual cause of this type of stability. Basically, this is related with the control functions, because if your generating units is here due to the control of that particular unit and it is oscillation, then it is called control modes. Mean due to the control, because there are various control in any generating units. It is your excitation control, it is your governor controls, either other, let us suppose you have some other extra devices like HVDC terminal is going on, and there we are having some SBC, etc. So, all the controllers here, they are oscillating to each other, and that is basically it is called control modes of oscillation. Another mode of oscillation is the torsional modes of oscillation, and those are associated with the turbine governor shaft system rotational components. Instability is caused by interaction with the excitation control, speed governors, HVDC control, and series compensated lines. So, this is the torsional modes of oscillation. So, torsional mode of oscillation can be understood by knowing this generating station is driven by the various type of turbines. It may be your high pressure turbine, it may be your low pressure turbine, it may be your intermediate pressure turbine. Again, depends upon the size of the generating power plant. It depends upon whether we are going for the 3 stage or 2 stage. Let us consider a big power plant which is having units of 500 or 200 megawatt. So, this is your synchronous alternator which is rotated by the turbines, and all the turbines here we can say this is your IP, this is your HP, means high pressure turbine, that is coupled with another shaft, and we are having here your intermediate pressure turbine, that is your IP, and then we are having your LP, that is a low pressure turbines, and then here it is connected with your shaft. So, this is your LP, low pressure turbine, and then we are getting here 3-phase supply, 3-phase power system that is connected. Here we know this your steam is coming here to your IP, and once it is expanded, here it is going out, again your pressure is coming here, and then it is going out, and finally it is coming here. Normally again it is going to be reheated, and then finally it is coming here, and this is your boiler. So, we have here shaft, and that is all this HP, that is high pressure turbine, intermediate pressure turbine, low pressure turbines, all are on the same shaft where your alternator, that is a synchronous machine, is connected. So, we have here the 4 rotating mass. So, all these 4 rotating mass, they are connected with the shaft, and that shaft is having some stiffness constant, it is not infinite. So, they are behaving just like, if you will take this example here. So, this one mass, it is connected between a spring and here is another mass. So, here it is rotating and that another is opposing, and then finally another mass here, and then it is, and so on and so forth. So, what is happening? If we analyze, then we will have some critical frequency corresponding to all these masses. So, here we will get the 1, 2 and 3, the frequency will be arising, and that is called the torsional modes of frequencies, and that is some oscillation. So, this frequency, if your system is here from 0 hertz to your operating system is 50 hertz, normally we will find some frequency if we analyze complete system dynamics including the turbines etc. as well, then you will find some here you will find at the range of 2 hertz, and the remaining you will find intermediate less than 50 hertz other cycles. So, these basically frequency of oscillations are the torsional modes of oscillation. Normally one term is very popular, subsynchronous resonance, because if your system which is a compensated transmission line, there is a possibility that due to this here some synchronous, some frequency, that is the current which is entering in the system, that may coincide with these frequency of oscillations, and then there will be huge resonance. What will happen if there is that frequency is matching with the torsional modes of frequencies, then there will be huge torque that is developed inside the shaft, and the shaft may be broken, and that is called your subsynchronous resonance, because at that frequency the resonance has occurred. So, this is basically your torsional mode, and here this is your, that's 2 hertz as I said, is a local oscillation mode. So, this is your torsional mode of oscillation. Now, let us again go back to the various stability phenomena, and that is defined as a transient stability, as already I discussed the small signal stability means small disturbance stability concern. Here the transient stability is also known as the large disturbance stability, and it is the ability of power system to maintain synchronous when subjected to a severe transient disturbance. Severe, again the severe, I am just telling from beginning that it may be your 3-phase fault, it may be severe power outage, and it may be other type of faults, it may be trimming of some severely heavily loaded transmission line, then your transient stability phenomena will occur. In this case, we cannot linearize the system, and we have to solve the system with the taking the non-linearity of the system as well. So, the instability here depends on the both initial operating point as well as the severity of the disturbance. So, we have to go for again the modeling of the load, modeling of the power system including your generator system, including your excitation system, and that will be clubbed together, and then we have to analyze. Normally this transient stability phenomena we normally go up to 3 to 10 seconds. However, the small signal stability phenomena analysis is required up to 10 to 20 seconds. Another is your dynamic stability concern. It is used for the small signal stability with automatic voltage regulation. As I said, the small signal stability again can be with the voltage regulators, AVRs, or without AVRs. But now this dynamic stability concern is not raised, and IEEE as well as the SIGRE recommended that it cannot be used the dynamic stability, because most of the power generating stations, they are equipped with the AVRs. So, there is no question of talking about this with or without AVR. So, whatever we are going to make analysis with the AVR, that is your small signal stability if your disturbance is small, and if your disturbance is severe and transient in nature, then we have to go for the transient stability analysis. Again, the stability phenomena, as I said, it depends upon the severity of the disturbance we define, and again this definition I am talking about the angular stability. So, from the looking at the point of view the severity of the system, severity of the fault, we categorize into the two. One is your small signal, that is a small disturbance, and another is your large disturbance or your transient stability. But if you are going for the time frame, then it is called the long term stability, and it is your another is your short term stability, or it is your medium term stability. Long term stability and the mid term stability are now new in the power system stability, and that is basically due to the frequency stability I will come to the total background of the stability phenomena, and we will see the various again at concise way. So, long term stability focuses on slower and the longer duration phenomena that accompany large scale upset that invokes the action of slow processes, controls and protection schemes. Basically, in the power system there is various protection schemes, and if they are activated, due to those there may be different control actions. This is a slow and the longer duration phenomena occurs. So, it is called long term stability phenomena. This phenomena include your boiler dynamics. You know the boiler dynamics, all this mechanical device, you must be very much careful. All the mechanical device including your governors, boilers, penny stocks, conduit dynamics, they are basically having the high time constant, large time constant compared to your electrical system. So, if you are going to include and they are going to impact your stability of the system, then it is called your long term stability phenomena, and then you have to take into account the various the dynamics like boiler dynamics, governor dynamics, etc., along with your AGC, power plant, transmission system protection and controls, transformer saturation, of nominal frequency effects on the loads and the networks, all if they are going to included in the long term stability phenomena. In the mid-term stability represents basically the transition between the short term and the long term responses, and it focuses on the synchronizing power oscillations between the machines, including the effect of some of the slower phenomena and possibly the large voltage and frequency excursion. Here the large voltage and frequency excursion, as I said, the frequency stability is due to the severe frequency deviation. So, if your frequency is suddenly changed, and normally this situation occurs when there is a lot of unbalance in the power and supply. So, if there is a large excursion in the voltage and frequency, then your this type long term and the mid term stability is concerned, and normally they come into the now in the new definition, they are coming in your frequency stability concept. So, typical time range, if you can see, for the short term or your transient, it is 0 to 10 second. For mid term, it is 10 to few minutes, and for long term, it is few minutes to tenths of minutes, normally this time of range of interest. So, if you are analyzing the long term stability, then you have to go for the several minutes. If you are going for the short term, then it is few up to 10 or to 20 seconds. Long term stability concerned with the system response with the major disturbances that involves contingency beyond the normal system design criteria. Now, one thing we should always be concerned, it is not possible to design a system that can sustain all the possibility of the contingencies, all the possibility of the faults. So, it is, and again, if you are going to design a system that can sustain all the possibility, all the faults, all type of trippings, all the consideration, then it is not possible, and it will be very, very expensive if you are going to design that. So, what we normally go, we normally try to analyze the system with the most probable and the credible contingency in the system, and based on that we analyze whole your stability phenomena. You can say it is your transient, small, frequency or voltage instability as well. So, the classification of stability analysis, the analysis of stability problem, identification of essential factors that contributes instability, and the formation of methods to improve stability are generally facilitated by classification of stability. So, the classification are based on the following, that the physical nature of the resulting instability, the size of disturbance considered, the devices, processes and the time span of your analysis, and most appropriate method of calculation and the prediction of the stability. Here this calculation methods are also very, very important. Sometimes your calculation method, because all these methods we are normally, suppose some stability, while designing you are analyzing your system whether your system will be stable or not, then you have to solve certain sets of differential equations. So, for the solving the differential equation, there are various methods, and again these methods are very much related with their initial guess. So if your initial guess is very bad, then there is a possibility that you will not get the stable solution, but the system is effectively, it will be stable. So it doesn't mean that your solution is not giving you a stable solution, you can say your system is unstable. So the appropriate calculation methods are also very important, that which method you are applying, what is your initial guess, etc. That should be very close to your post disturbance equilibrium, and again which type of stability you are predicting. So what is the type of fault, what is the size of the disturbance considered, what are the devices and processes that are going to be considered. So these all are included in the classification of the stability problem. So far we have seen the various type of stability classification, and again now I can summarize. So you can see the power system stability here in this diagram. It is basically can be categorized in the three groups. One is your angle stability, where we are concerned about the delta. Another is your frequency stability, it is basically related with the frequency, and another is your voltage, that is a voltage stability. So again this angle stability can be classified into the two categories. One is your transient stability and another is your small signal stability. Again, to remind you, the transient stability is also called your large disturbance stability phenomena, and the small signal is your small disturbance stability phenomena. All these two are basically related with the short term stability phenomena, and this basically related with your this normally required 3 to 5 seconds, and here we go for the 10 to 20 seconds. So whole this analysis is, if you are going for the time frame, then this your angle stability is your short term phenomena, because it is less than 1 minute. Again this small signal stability can be classified into the two group, as again I have explained. One is your called the non-oscillatory instability and another is your oscillatory instability. Here non-oscillatory instability is due to the insufficient synchronizing torque. If the automatic voltage regulators are not there, then this concern arises. But nowadays most of the generators, they are with the AVRs, that is automatic voltage regulators. So oscillatory instability is the major concern in the modern power system, and this is due to the insufficient damping in the system. And if there is insufficient damping torque, so there will be some sustained oscillation in the power system, and if that oscillation is keep on increasing, then it is called oscillatory instability. But if this oscillation is keep on reducing or is stable, then is not increasing, then we can say the system is stable and it is oscillatory stable. Again here that oscillatory instability can be classified into the 4 categories depending on different criteria. First one is your local, or you can say plant modes. Again I said that it is due to the one plant, one unit oscillate respect to the rest of the system. Here inter area means two areas are oscillating to each other, again due to the weak tie lines. And the control modes, if any power station there is various controllers are there and if they are oscillating, then it is control modes. And the torsional modes, due to the rotating mass, different turbines are there and they have some critical frequency. If there are some oscillations of critical frequency between that, and that is called your torsional modes. To come to the frequency stability, here it is your mid-term, or it is included in the short term, and then another is your long term. Long term, here when we go for the long term stability, basically it is again the within here the mid term it is less than 1 minute, and long term it is more than 1 minute, it is known. Here what we in the long term, normally we take the dynamics of your boiler, your governors, all the dynamics and slower dynamics process, if they are included, then it is called long term stability. Here in the frequency stability, basically it is due to the huge excursion again of the frequency in the system. Normally if the system becomes islanding, there is unbalance in the real and reactive power, huge power, then we can say this frequency stability phenomena is occurring, or you can say system is frequency unstable. Another third one is your voltage stability, and that voltage stability can be categorized into two parts. One is your large disturbance voltage stability, another is your small disturbance voltage stability. Here again based on the disturbance. So if the disturbance is severe, then if you are analyzing your stability, then it is voltage stability with the large disturbance, another is your small disturbance voltage stability. So, large disturbance voltage stability just like a large disturbance, that if there is a tripping of transmission line, tripping of your generators, or there is some three-phase fault, then it is, if you are analyzing, then it is voltage stability with the large disturbance. And for the small disturbance means if there is a change in the smaller loads, there is a smaller change, gradual change in the voltage, etc., then it is called the small disturbance stability. Again, this voltage stability in terms of time frame, here just I have taken combined together, means we have two type. It may be short term voltage stability problem, or it is your long term voltage stability problem. The short term voltage stability involves the dynamics of fast acting voltage components such as induction motors, electrically controlled loads, and HVDC converters. The steady period of interest is in the order of several seconds, and analysis requires the solution of appropriate system differential equations. This is similar to the analysis of rotor angle stability. Dynamic modeling of load is often essential in this case, and in contrast to angle stability, the short circuits near load are important. It is recommended that the term transient voltage stability not be used. Normally we should not say it is a transient voltage stability. So, always we have to call it is a short term voltage stability. In the long term, here the voltage stability involves the slower acting equipment such as the type changing transformers, thermostatically controlled loads, generator current limiters, etc. The steady period of interest may extend to several or many minutes, and long term simulations are required for analysis of the system performance. The stability is usually determined by resulting outage of equipment rather than the severity of initial disturbance. Instability is due to the loss of long term equilibrium when the load try to restore their power beyond this capability of the transmission network and connect the generation. The post disturbance steady state operating points being small disturbance, unstable, or a lack of attraction toward the stable post disturbance equilibrium. Now, so this is complete your power system stability definition, and then broadly you can say broadly classification of the power system stability. To again to go for the next chapter and next lecture of this module, let us see the history of system stability problems. So, historical review of stability problems or review of the history of the stability is useful for the better understanding of present day stability problem. So, power system stability was first recognized as an important problem in 1920. The first laboratory test was reported on miniature circuit in 1924. In 1925, the field test on the practical system, means first field test on the practical system they reported, means first reported test on the practical system. Early stability problems were associated with the remote hydro generating stations connected with the long distance transmission line, because earlier the hydro generators were very prominent, and then we had a long generating transmission lines, and then it was associated with the long distance transmission side. So, slide rules and the mechanical calculators were used at that time, hence the formulation were simple. Generators were taken as a simple voltage source behind the fixed reactances, and the loads were taken as the constant impedance. In early 1950s, electronic analog computers were used. In 1950s also saw the digital computers. So, first digital computer program for the power system stability analysis was developed about 1956. In 1960s, utility interests were on the transient stability. So, before this 60s, people were only concerned about the transient stability. Due to the increased loading and interconnections, the power system exhibits the oscillatory instability. Proper modeling concern arises. The significant R&D work has been undertaken in the last few years to gain better insight into the physical aspect of these new stability problems. So, nowadays we are going more and more detailed modeling, calculations, and then we are analyzing the system stability concern, and then we are designing our power system based on those criteria. Thank you.